Okay, second in the series of organic chemistry reactions to know are the addition reactions of alkenes. So first off, alkenes are more reactive than alkanes. The reasoning being that second bond in the C to C double bond is a pi bond, and that's a weaker bond than the original sigma bond that is between the carbon atoms. So the pi bond is more reactive. Or if you're not an HL, the second bond is not as strong as the first bond, and it leads to alkenes being far more reactive than alkanes. The general reaction that is an addition reaction is very simple. Something gets added to this molecule. It's going to end up, instead of the carbon to carbon double bond, that second bond is going to go away, and two things are going to add. So right now we're calling them X and Y. X will get added to one carbon, Y will get added to the other. And that's always how the addition reactions happen. Okay? There are 5 different addition reactions to know. They each get special names, special conditions, special uses. Okay? So the first one that I've written here on this little chart is adding 2 bromines. That gets my favorite name of any of these reactions. It's called bromination. And no special conditions are necessary. All you have to do is add a Br2 to a solution that has carbon-to-carbon double bond, and the bromine will very quickly add across that double bond 1 bromine to each carbon. I'll come back to the uses of these in a moment. If we add hydrogen, so if we add H2, then we call it hydrogenation or hydrogenation. The special condition needed in this is a nickel catalyst, and heat is also needed. This next one is when you add a halogen onto this molecule. Along with the halogen, you add a hydrogen. So it's not called like bromination or chlorination or iodination, which this one would be called when you add 2 of that halogen at a time. We're just adding 1 halogen, so we call it halogenation. And so all you need for this is hydrogen halide, so HCl, HF, HBr, HI, and the H and the halogen will attach. So I'm using X here to stand in for generic halogen. As far as I know, there's not really any condition needed for this. If you were stuck and they asked you for a condition, when in doubt, you can always say that heat is recommended because it makes reactions go faster. But in general, not really anything special to remember about that reaction. This one, we're adding H and OH. Well, HOH is the same as water, so really we're adding H2O. We are adding H2O in the gas phase, so this is going to be called steam. And the special conditions needed is H2SO4 as a catalyst. So you do need to remember these extra little details, which is kind of a pain, but you can do it. So that's what's needed for this one. Because we're adding water, we're going to call it hydration. A lot of people want to call this one, where you're adding hydrogen, hydration. So you have to remember adding hydrogen is hydrogenation, adding water is hydration. This last one, you're not really adding anything new. What you're doing is adding the alkene to itself. And by doing that, you're going to make a super duper long chain of repeating units, which we call a polymer. So this reaction here is called polymerization, or addition polymerization. This is how we make plastics. So there's nothing really to add to it except itself, and it just gets repeated in a super duper long chain. So those are the 5 reactions. So bromination is used as a simple lab test to distinguish alkanes and alkenes. Alkanes, if no UV light is present, will not react with bromine. Bromine has a very distinct red-brown color, so the red-brown color remains. If you have an alkene, the alkene reacts very quickly to decolorize bromine, and it goes clear. So it's not a super high-tech test. I'll show you it in the lab. You basically just add some bromine or some bromine water to these 2 different test tubes, and you shake them up, and if the color disappears, you know that there must be a carbon-to-carbon bond present or an extra bond present. If the color remains, that implies that there are no carbon-to-carbon double bonds because it doesn't react. Hydrogenation, the one with the nickel catalyst and heat, this reaction gets used to produce margarine. No, I'm spelling that wrong. There we go. Margarine and semi-solid cooking oils. If you've ever seen hydrogenated vegetable oils on an ingredient label, this is what they were talking about. They literally take unsaturated fats, which we call oils, they add hydrogen to them, and that causes them to turn into more saturated fats. So we are unnaturally saturating the fats. That helps straighten the carbon chains in them, and that leads to more London forces, and it leads to higher melting points, which is why they go from being liquids to being solids. So hydrogenation is used to make margarine. Halogenation, you don't need to know any uses for this. It could be used to make halogenoalkanes, which could then be used to make other things. So I guess you could say it's useful to make halogenoalkanes. Halogenoalkanes are used in refrigerators and air conditioners and things like that. But for us, it's kind of going to be useful as one step in a chain of reactions if we're trying to make a certain product. Hydration is useful for making industrial ethanol and other alcohols. So we use yeast to make ethanol for drinking, but if you want to use 95% ethanol in the lab, they do that by taking ethene and they hydrate it to make it into ethanol. And then you've got addition polymerization, which is really useful for making plastics. Obviously, the issue is plastics don't biodegrade, so they fill landfills and they release bad chemicals when burned. So they tend to not burn very completely, so they're releasing some kind of nasty, unhealthy stuff when they get burned. They can be adapted to have amazingly diverse properties, so highly useful, and it's a big money industry as a result. But plastics don't ever biodegrade. That means that any plastic you've ever used is still on the planet and will be on the planet for hundreds of years, and that's kind of a scary thought. So they're highly useful, but they do have their downside. So here's how it looks. Just to go over addition polymerization more closely, it's probably the trickiest of the five because it's a little different. Whatever the alkene is, that's called the monomer. It's going to be the repeating unit, something that gets repeated over and over. And then the polymer, in the polymer, the C to C double bond gets removed. And instead of that double bond, the one that's here, you end up with a bond sticking off of each carbon in either direction, linking up to the next monomer. So you could think of this chain here. Here's a single monomer unit, and then here's the next monomer unit, and then here's the next monomer unit, and I think you get the idea. So this is a chain of what's called polyethene or polyethylene, what's in very simple plastic bags, because you've taken ethene and you've polymerized it, and so now we would call this polyethene. Or the old name for it is polyethylene. This right here is what we call the repeating unit. So sometimes you get asked to draw that. You just have to put the parentheses, the bonds continuing through the parentheses, and the little n to show that it could repeat any number of times. This is a section of the polymer that shows 5 units. So let me just distinguish those things. /10 carbon atoms, right? That's one thing the IB would ask you to do, is draw a section of the polymer with a certain number of units or carbon atoms, or they could ask you to draw the repeating unit as I've drawn, or I've found here, okay? That's what's shown here. So again, here's another one, tetrafluoroethene. Well, that gets used to make Teflon, to coating on nonstick pans. Again, to make the repeating unit, get rid of the second bond and add a bond sticking off of each carbon. You add the parentheses and you write N. So you're just saying this unit gets repeated thousands of times, any number of times. And this would be a section of the polymer, again, with, it looks like 5 repeating units because it has 10 carbons. And then this one, chloroethene, And here we have the repeating unit, and then here we have a section that has 6 carbons or 3 repeating units. And this gets used to make PVC, polyvinyl chloride, which has a variety of uses. That's all there is to know about the addition reactions. You have to know, what can get turned into what. So what different things can you add onto the alkene, what those reactions are called, what their uses are, and if there are any special conditions needed, like a catalyst or heat. The questions themselves are not too bad, like what is the product of the reaction between propene and steam? Well, the reaction of propene and steam would be C3H6. Steam is H2O. And if you know that propene is an alkene, it's going to undergo addition, and you just have to figure out how to add this on. So now it becomes C3H7OH. So you've added a hydrogen onto one carbon and an OH onto the other carbon. That's from the H2O. And so you've made propanol as the main product. The chemical equation between ethene and hydrogen, C2H4. Obviously, you got to know your functional groups at this point, so you can come up with from ethene, it's C2H4 plus H2, and that's going to make its addition, just add it on, so that makes C2H6. Okay. The condition needed would be nickel catalyst, and you could probably say heat as an extra condition, but they'll definitely be looking for nickel. When you write the chemical equations, you do write these condensed formulas. You generally don't draw out the structural formulas unless you're instructed to do so. Like in this one, determine the structural formulas of the 2 possible products of the reaction of hydrogen chloride and butanene. Well, if it's butanene, then you've got C to C double bond first, then a carbon, then a carbon, and you're going to add the HCl. Okay? The reason why there are 2 possible products is that the chlorine could add on to this carbon, but it could also, that's not an arrow. The chlorine could add onto that carbon, and it could also add onto that carbon, and the hydrogen would add onto the other one. So your 2 products by name are either going to be 1-chloro or 2-chloro-butane in the end. I'm not going to draw them because it's hard to draw with this trackpad, but we'll review these in class. These are the types of questions that you get asked. They really are fairly simple. Addition's probably the simplest of all the reactions that we know. For HL, you're going to learn a mechanism for it that's more complicated. But the straightforward content is to just know which different chemicals can get added to the carbon-to-carbon double bond, and being able to write out chemical equations or structural formulas for the products, and knowing the names of the reactions and the uses for them.